Hmm.
After 4 days of good food, coming back to DC was such a shock.
Yeah. Yeah, the DC's fine. But just fine. I'm sure I would like to hope it's better than it was when I went to it 20 years ago. But it's probably pretty much the same. It's not like food's changed a whole lot.
I think I actually cried happy tears when I had food. I was like, food can taste good. I don't remember. Right? Yeah.
That is correct. You have 33 days to run 68 more miles. What's that? Oh yeah, I got it.
Do you runner?
I am. I mean, I would. Yes, I would say I'm a runner. My goal this year is to run 1,000 miles. I'm currently at 932, so I got 68 to go. I think I'm gonna make it.
You got one of the I run off that you got one of the.
It does not watch.
Okay.
Yeah, it's good. I like the Strava app. That's what I typically use to record things. What was I doing? Oh, yeah, I'm sharing the screen. Okay. Oops. I have to come up with a goal for next year, though. Smaller.
Also, chocolate Germany. Yes. Because, and since I thought I was gonna be going yesterday, I was taking them all day yesterday. And so then I had to be on.
I ended up finding a day.
Yes, because my flight was delayed by 5 hours.
Oh, that's a
yesterday. I was
bummer.
like, I'm not gonna land here at 11:35.
Yeah, that's pretty late.
So I was like, I'll just take a 7-8.
I'm glad you made it. Why do you do this? What is going on now? Okay, that's weird. Sorry, technical difficulties. Okay.
I absolutely used the mini for ginger ale. I was gonna bring it to me. I just gave me the whole can. And I was like,
That was nice.
what's up? They might ask for the can. For some reason, I thought it was like illegal. I don't know. They gave it to me and I was like,
Sometimes they will, sometimes they won't. Depends on how nice they feel.
I got lucky because there was so much turbulence, they had to cancel the flight service for the entire flight. So I was the only one who drank it.
Oh no.
I was like,
Oh yeah, I should turn on my video. There we go.
James, you're muted.
Thanks. Got it. If that's an issue in the future, not that, I mean, it's only got a week left, but right, I don't always see the chat right away. You're always welcome to unmute yourself and say words. It'll terrify me probably, but at least then I would be unmuted. So, all right. So we're just talking about problem 2 from the section 9.1. Find the probability of the chosen person going to college. This ends up being 35 out of 73. Now, a real quick answer to the second question is, well, what's the probability of the chosen person not going to college? If you're trying to find the,
Can't be set for a time of day.
okay, I wasn't trying to set a timer. That's interesting. It's just gonna be 1 minus what we found. So if this is the probability of going to college, then we're doing 1 minus the probability of going to college, which is 1 minus 35 over 73. And you can simplify that in whatever way you want. You could also just enter that into WebWork, which is fine. So the way I might look at this, if I was trying to actually be more systematic about it, as opposed to just write stuff down, is I might actually make like a little kind of table. You could also make a Venn diagram, I suppose, but I feel like a table here is actually better. So we've got girls, boys, going to college, not going to college. And so we know that there are 48 girls total, 20 of them are going to college. So we have 21 girls going to college. And then the ones that are not going to college, well, there's 48 minus 21. So that's going to be 27 of them not going to college. For the boys, there are 14 who are going to college, and 25 minus 14 is 11 who are not going to college. And what's nice about this table, which you will definitely see this kind of table in a stats class, is the totals in each row and column should add up to what they are supposed to be, meaning the 21 girls who are going to college plus the 14 boys going to college should add up to a total of 35 who are going to college, and a total of 38 who are not going to college. Similarly, the columns add up to 48 who are girls, and 25 who are boys. And if you add those up, you get 73. So here, if we're trying to find, what was it? The probability the person chosen is a girl who is not going to college. So the probability of being a girl and not going to college, that's the intersection notation. This is often how it's written in other classes. I'm just trying to find the people who are both girls and not going to college, which are these folks right here. So it's going to be 27 out of 73. You could probably do a tree diagram here. If you really wanted to, you could make the first branch in the tree being a girl or a boy. And then the second branch, and so the probability of being a girl in this particular thing is, let's see, there are 48 girls out of 73, and there are 25 boys out of 73. And then the next branch in your tree would be college or not college. But I feel like this gets a little dicier because here when talking about college, you're saying, well, okay, of the 48 girls that there are, what is it, 21 out of 48 who are college bound, and the other 27 out of 48 who are not college bound. Similarly for boys, 14 out of 25 who are going to college and 11 out of 25 who are not. So if you wanted to find the probability of being a girl and not going to college, you'd have to take the probability of being a girl, 40 out of 73, and multiply by the probability of them not going to college, which would be 27 out of 48. And then the 48 would cancel, and you'd still be left with 27 out of 73. That would work too. I feel like a tree is less obvious the way to go here, but it could work. The thing about a tree, which you will maybe see in the future, is that it's kind of a tree of conditional probabilities, meaning everything that's happening along this branch is conditioned upon for the first thing being that the person was a girl. So person is a girl, and then this probability here is the probability of going to college given that the person was a girl, or the probability of not going to college given that the person was a girl. So all these later probabilities are what are called conditional probabilities. Let's see this question. Let me extend this so I can read it better. Maybe we'll see here. Whew, wow, that's a lot of text. Okay, I have a question on how to do problem 1 from the same set. To understand how to visualize the info they have given us and make it into a table. Example problem 1. Yeah, sure. So let's see. Oh yeah, we actually we did one. I think we did this one last time. Could be wrong. Do it? Yeah. So what I would say, not to use last time, do the same thing again. But definitely refer to the video that is posted from last class on Wednesday. Yeah, I was going to get to 9.3. That's where I was definitely headed. I just wanted to make sure that someone had a question about 9.1, but 9.3 was the direction I was headed. So, so to the person who wrote the first thing there, I would say definitely go check out the video from last class. I definitely go over that example. Oh yeah, 9.3. So 9.3 definitely needs us to talk about a few special probability density functions, because that's what 9.3 is all about. And I would really say for 9.3, most of 9.3 is kind of about memorizing some stuff. Like you can definitely, the process is still going to be the same as far as how we find the expected value and the variance and the standard deviation, but it's going to be so repetitive for some of the examples that we kind of, there's a nice easy way of finding it for the 3 different types of special probability density functions that occur in section 9.3. So we can also come back around section 9.2 if there's any questions there, but they're very kind of related. So let's look at the special probability density functions. And just to remind myself, sections 9.3 and 9.2 are due on Wednesday, right? Is that correct? I think they are. I think I saw the due date. Let's see. Yeah, 11. Yeah, November 30th, the last day of November. Special probability, missed the word, density functions. So there are 3 such functions that your book covers. Sorry if that's hard to read. The one that I would say is probably the most used and the most interesting is the exponential one. So the first one is an example like the following. The lifetime T in years of a battery is an exponential probability density function. Exponential is the word we should focus on here. Okay. With the following function, f of t is equal to 1/3 e to the negative 1/3 t on the interval from 0 to infinity. So technically, the life of the battery could go on and on and on and on and on and on and on. At some point, it's going to stop, but we don't know when, and it could last a really long time. So that's why there is no real upper bound, right? No one's going to say, well, the battery's only going to last 10 years. Maybe it's a really long life battery. Who knows? Sometimes batteries last a really long time. And I replaced a laptop battery one time, and the guy was like, "You've had this laptop for how many years? And you're just replacing the battery the first time?" I'm like, "Yeah." He's like, "Wow, you got a lot of life out of there." So you never know. So the thing about this, well, let's actually do some example problems. Oh, the thing I want to say is this number here, this coefficient, and this coefficient of t here should always be opposite values. If that's 1/3, that's -1/3. If that's 4, that's -4. Whatever that is, that's going to be the negative of it. Always has to work that way. So the first thing we want to do is, find the probability that the battery lasts 2 years or less. I should point out that question, as far as a continuous distribution is concerned, is the same question as asking to find the probability of the battery lasts less than 2 years. What I'm saying is the probability that the time the battery lasts is less than 2 years is the same as the probability that the time the battery lasts is less than or equal to 2 years. Because it actually living for exactly 2 years is a 0% probability, because it's this finite thing in this infinite realm of possibilities. So, right, if someone said, what's the probability that the battery lasts exactly 2 years? Well, when it's a continuous probability density function, you find the probability by doing what? The integral from where to where? Well, if I want it to be exactly 2 years, it should live at least 2 years and at most 2 years. And if that's my integral from 2 to 2, it's going to be 0. So that's why the probability for a continuous function that actually equals a specific value is 0, because you're just doing the integral over an interval that has no length. So that's why these are the same. So to calculate this, it's going to be the integral from 0 to 2 of 1/3 e to the negative 1/3 t dt. And you could do a u sub. I guess we could. If we did the u sub, u equals negative 1/3 t. Our du is negative 1/3 dt. And we get negative 3 du equal to dt. So our integral becomes the integral of 1/3 e to the u times a negative 3 du. And those 3's cancel, and you just get the integral of negative e to the u, which is negative e to the u, which is negative e to the negative 1/3 t. Which again, if you think about it, if this is negative e to the negative 1/3 t, makes sense, because if you took the derivative of that, you would end up multiplying by a negative 1/3, which would give you exactly the positive 1/3 out in front. From 0 to 2, which ends up equaling negative e to the negative 2/3 minus negative e to the 0, which ends up being 1 minus e to the negative 2/3, which is approximately 0.487. So there's about a 49% chance that the battery lasts less than or equal to 2 years. Okay. Now here's the more interesting question, or the question that we want to have already done this part for to calculate. If I can move the paper. Maybe I can, maybe I can't. What's the probability? Probability was a shorter word. That the battery lasts longer than 2 years. Well, if we weren't being very thoughtful about it, we would just say, okay, it's going to be the probability that t is bigger than 2, which will be the integral from 2 to infinity of 1/3 e to the negative 1/3 t. And while you could totally do this, we typically don't want to unless we have to. I would rather not do an improper integral unless I was absolutely forced to do it. So what you should do here is say that's going to be 1 minus the probability that t is less than 2, which is going to be 1 minus the integral that we already did. And that's what I would typically recommend. If you're trying to find the probability that some time is greater than some number, and you have to go to infinity, do the complement. Do 1 minus the probability that the time is less than that number. So here, that's just going to be 1 minus the thing we already calculated, which is going to be e to the negative 2/3, which is approximately 0.513. Which makes sense, right? The probability the battery lasts less than 2 years is about 48.7%. Probably lasts longer than 2 years is about 51.3%. They have to add up to all of the probability, which is 100%. Okay. Graphically, right, here's what we've got. If your function looks like this, which it does, here's your f of t equal to 1/3 e to the negative 1/3 t. Here's the y-intercept at 0, 1/3. And this is like 2 right here. This area to the left, that area is the probability that time is less than 2. And this area to the right is the probability that time is greater than 2. And they have to add up to 1. Cool. Now, so those are things that there's no real nice formula to just know the answer to calculate them. Right? Finding the probability the time is longer than some amount, less than some amount, you just have to do the interval. But you should definitely, for ones where it's greater than, you should definitely do this kind of deal. I definitely recommend that. But then there's other things you want to calculate, like the expected value. So and I'm gonna want more room. Don't keep yourself, James. So I want to find for f of t equal to, again, it was 1/3 e to the negative 1/3 t. I really would like to find the expected value or the expected length of time the battery will live. So reminder, whenever you're calculating expected value for a continuous random variable or continuous probability density function, whatever you want to call them. My terminology here is not the best. It's always just the integral over the entire interval of your variable times your function. In this case, from 0 to infinity. We are going to have to do an improper integral here. There's no way around it. Not too terrible. So in this case, we're doing the integral from 0 to infinity of t times 1/3 e to the negative 1/3 t dt. Now, the thing that is terrible, in my opinion, is that we have to also do an integration by parts. Kind of stuck. So, interesting. Oh yeah, sure. Yeah, all right. So let's do just the nice integral off to the side here before we deal with all the improperness. So we're going to do the integral of t times 1/3 e to the negative 1/3 t dt. And I'm going to let u equal t and dv be the rest. And I would probably pick I would probably include the 1/3 with my dv. I wouldn't maybe always do that. Maybe, I don't know. I guess I would here because I already know what the integral is. Right? I just on the previous page did the integral of this part already. So it doesn't seem so bad. So my dv is going to be 1/3 e to the negative 1/3 t dt. My du is 1 dt. My v is the antiderivative of this, which we just saw was negative e to the negative 1/3 t. We literally just did. So then my integral here is going to be uv, so negative t e to the negative 1/3 t minus the integral of v du, which is the integral of negative e to the negative 1/3 t. Negative is positive. So this is going to be equal to negative t e to the negative 1/3 t plus the integral of e to the negative 1/3 t, which is again going to divide by negative 1/3. So we're going to end up getting minus 3 e to the negative 1/3 t. You can check, take the derivative of that piece, you end up multiplying by a -1/3. So you would get -3 times -1/3, which is +1 times e to the -1/3 t. Questions? The question you should be having is why are you writing dt? Because I shouldn't be. Sorry, yeah. I could probably try to turn that into a plus c if I really wanted to, but let's leave it at that. So now back to this. This is going to be equal to the limit, as I shouldn't use t because t is already being used in this problem. So pick any other letter in the alphabet. I probably pick b. Limit is b goes to infinity of the integral from 0 to b of t times 1/3 e to the -1/3 t dt. And then we're just going to write that over there. So we're going to take this, and that's what's going to go there. So we're going to have the limit as b goes to infinity of. Now here's where I might do a slight rewrite. I really, really recommend writing this so that your powers end up going to positive places. And since I'm going to be plugging in a very positive number, e to the -1/3 times a positive number is going to give me e to a negative power. I would much rather write this as -t over e to the +1/3 t and -3 over e to the +1/3 t. It's going to help me see what happens better. So I'm going to write this as the limit as b goes to infinity of so much writing. -t e to the 1/3 t -3 over e to the 1/3 t. Wow, that's a terrible looking 3. From 0 to b, and then we're going to do the limit as b goes to infinity. Something interesting to consider here before we get going, before we finish this. We would expect there to be an answer to this question, right? If I said, this battery lives, from 0 to infinity years, we would expect there to be some average lifetime or expected lifetime. So we should be fairly able to convince ourselves that this is going to converge. Like, we don't have to check it's going to converge, it's going to converge, but it's still kind of interesting to think about. Plugging in my b's, I get -b over e to the 1/3 b -3 over e to the 1/3 b minus, plugging in my zeros, I get 0 over, doesn't matter because it's not 0, -3 over e to the 0. Okay, so now you'll have to remind me all. I assume, but I'm not 100% sure. Did you or did you not learn L'Hopital's rule in 16A? Did anyone learn L'Hopital's rule? Did anyone not learn L'Hopital's rule? It's okay. Okay, so we'll just go with the not learn L'Hopital's rule because so here's what we're going to do. As b goes to infinity, we can certainly see that this part here is for sure going to go to 0 because the denominator is getting infinitely large and the numerator is 3. And 3 divided by an infinitely large number is going to get infinitesimally small. Now, the same thing is also somewhat true here. The denominator is getting infinitely large. The numerator is also getting infinitely large, but at a much slower pace. So this part here, as my friend Grant likes to write, is an infinity over infinity. That bottom infinity is way bigger than that top infinity. I know, they're both infinities, but the bottom one really outpaces the top one. Now, if you know how to use L'Hopital's rule, you can use L'Hopital's rule here, take the derivative of the top, the derivative of the bottom, and take the limit of that and see that it's going to go to 0. But if you don't know L'Hopital's rule, or if she doesn't want you to use L'Hopital's rule, you can just say exponential functions always outclass polynomial functions all the time. And so this is also going to go to 0. So we end up getting 0 minus -3, which is 3. And yeah, I should say, just so you know, worth knowing that the limit as x goes to infinity of x to any positive power over e to the x is always going to go to 0. An exponential function is always going to overcome a polynomial function. Now, here's the short version of this. Yeah. I'm gonna write it like this. Sure, I can fit it in here. If your function your probability density function, f of t, is equal to, let me make sure I write it like the book writes it, because I always want to do it backwards, and I'd rather not do it backwards for all of you. Yeah, okay. If f of t is equal to 1 over a times e to the negative 1 over a times t. Sorry, that looks kind of terrible there. I feel like you can't. Let me try and fit things in here. Let me write this big. It's important. If f of t equals 1 over a times e to the negative 1 over a times t on the interval from 0 to infinity, then the expected value of t is a. Our function was 1/3 e to the negative 1/3 t, and the expected value was 3. Not a coincidence. It's how it always plays out, which is nice. So later on, when someone says, hey, my function is, I don't know, 8 e to the negative 8x, and they ask you, okay, what's the expected value of x? We should be able to say it's what lovely fraction? 1/8. I should say on the interval from 0 to infinity. It is important to state the interval. So that's probably the most used special probability density function, is this exponential one, and it's always true that the expected value is just equal to whatever that reciprocal of that first number out there is. So if it's 8, your expected value is 1/8. If it's 1/3, your expected value is 3, and so on and so on and so on. So then the fun part. If I wanted to find the variance would be, we're going to use the alternate formula, the nice formula, in my opinion. The variance is the integral, again, over the entire interval of x squared. I'm using x instead of t. I'll just go generally here. X squared times f of x dx minus the mean squared. So in this particular problem, we're not going to calculate it, so we have plenty of room here. The variance of t, since I was using t, would have been the integral from 0 to infinity of t squared times 1/3 e to the negative 1/3 t dt minus 3 squared. And it's a terrible pain, right? Because to do this integral, I just want to point out, to do this integral, you'd have to do integration by parts twice, which no one wants to do. And no one needs to do, because the nice thing here is that the variance here is going to equal 3 squared. The variance here is going to equal whatever your a squared is. So in a function like this, the expected value is equal to a, and the standard deviation is also equal to a. Which is great. And then the variance is equal to a squared. So that's what I would encourage you to remember about the exponential special probability density function, is that both the expected value and the standard deviation are the same number, and they're both that a number, which is the reciprocal of that leading coefficient there. Okay. One last thing about this, something else to calculate that is neither of these things we've talked about. What is the median battery life? Okay, so the median and the mean, or the median and the expected value, whatever name you want to use for the average, mean, expected value, all mean, the same thing. Whereas median is a different measure of the middle. The median literally separates the bottom half from the top half. That's what the median measures. Whereas the mean, or the average of the expected value, is a weighted average. So when I'm thinking graphically, and they're not too far from each other in this particular example, but basically the median, again, we still have the same function here. The median is literally the point, the time value, where half of the area is here and half of the area is here. On the other hand, just for to contrast, the expected value, which we found to be 3, the expected value is where this thing would balance if it was like a teeter-totter. And that's more like over here. Because I know the median here happens to be less than 3. So balance, average is like where the teeter-totter balance is, median is just where half the area is on one side, half the area is on the other side. So what do we do to calculate the median? Well, we're going to say, I want the integral from, you can either choose the hard path and say the integral from m to infinity of my function, 1/3 e to the negative 1/3 t. You can either set this equal to 1/2 and solve for m, or the much more normal choice, the integral from 0 to the median, whatever that is, which we're going to solve for, of the same function is equal to 1/2. So set that equal to 1/2 and solve for m. Which is kind of funky, but it's not too terrible. We've already integrated this thing at least a couple times here. So we know that this is going to just become, so the integral of this is negative e to the negative 1/3 t from 0 to m, and it's equal to 1/2. And then we plug in, so we get negative e to the negative m thirds minus negative e to the 0 equals 1/2. All right, let's see. Negative e to the negative m thirds plus 1 is equal to 1/2. I would probably subtract 1/2 from both sides and bring that over to the other side. So I'm going to get 1 minus 1/2 equal to positive e to the negative m thirds. And then I take the natural log of both sides. Natural log of 1/2 equals negative m over 3. And then I multiply both sides by negative 3. So negative 3 natural log of 1/2 equals m, or preferably 3 times natural log of 2 is equal to m. Which is approximately what? 2.07, I believe. I think. Let's check. Yeah, 2.07. And just to go along with the theme for this particular function of we already know all the things if we want to know them. In general, let me go back to this previous page here for a second. In general, the median is equal to a times the natural log of 2. Again, all these things are just true for this particular type of function. Not true for anything else. Okay. Let's take a look here. Let me see one thing. Yeah. So it looks like section 9.3, which is what people are asking about, it's a lot of like just calculating all these things. Like expected value, variance, standard deviation. Expected value, variance, standard deviation. Like I see 1, 2, 3 problems where you have to calculate those 3 things. And then, yeah, some other stuff. Okay. Yeah, only I guess one of these is really, so I'd say all the stuff we just did really applies to problem 6 on section 9.3. It's still good that we went over it. See how much time we got? Okay, not a whole lot. Let's look over here. The other special probability density functions. Do we need to talk about them? Maybe. Sorry, one sec. Are there any questions about this before I move on to something else? Someone? Oh, sure, yeah. Okay. All right. There are 2 other special probability density functions. One of them will probably never come up, and the other one is super boring. But we should talk about them both real quick. So the one that's super boring, and so I would say both of these people tend to mix up their names for some reason. So one of them is the uniform distribution, which is the super boring one. To talk about in a second. And the other one is I believe it's the normal distribution. Is that the word I'm looking for? I think so. Double check. Yeah. The normal, or sometimes called the standard normal distribution. Which, if you've ever taken any sort of stats class, you should be very familiar with. The standard normal distribution is just another word for the bell curve. Well, let's go back to the uniform distribution first. So the uniform distribution is super duper boring, but it is still useful. It comes up. Here's an example. The probability that a bus, there's a helicopter out there, will arrive in a 10-minute interval is uniform. Okay, what does that mean? It means that essentially any time is as likely as any other time. It could take the full 10 minutes, it could take 9 minutes, it could take 7.5 minutes, right? Any time is equally likely. So your probability density function is just a constant function. So if I'm thinking about doing the integral from 0 to 10, right? Because that's what I'm looking at. My function starting at 0 and ending at 10 of my function. Well, that integral should equal what? If I'm integrating over the entire interval, it should equal 1. But we just said it should also be a constant. So really, I should have actually written this as a k, not as an f of x. So the integral from 0 to 10 of k is equal to 1. But the integral of a constant is just the constant times the variable. And that's going to be the constant times 10 minus 0 equal to 1. That means my constant is 1/10. So my function here, my probability density function, is the kind of boring constant function 1/10. And my graph looks like this. That's it. It's got a height of 1/10, and the probability density function is just equal to 1/10 all the time from 0 to 10, and then it stops, right? Because there can't be anything, you can't wait longer than 10 minutes because the bus is guaranteed to arrive between 0 and 10 minutes because we're making up unreal situations. Here, the probabilities are super easy to calculate. Like the probability that it takes between, say, I don't know, 1 minute and 4 minutes. Well, that's a 3-minute interval. So that's going to be 3/10 of the probability will be 3/10 that the bus comes in that interval. We could do the calculation, interval from 1 to 4 of 1/10. Whenever you integrate a constant, you just end up getting the constant times the length of the interval. That's just going to be 1/10 times 4 minus 1, which is 3/10. So if a bus takes between 0 and 10 minutes and everything is equally likely, what would we expect to happen? Take as little as 0, as much as 10. One split the difference. The expected value is exactly going to be the average of those two. So here the expected value is going to be the integral from 0 to 10 of x times, bless you, 1/10, which is going to be x squared over 20 from 0 to 10, which is going to be 100 over 20 minus 0 over 20, which is exactly 5. So the nice thing here is that in general, for uniform distribution, and we'll give ourselves, we're going to take up all this room because the bell curve we're not going to do much with. So for a function that's more like f of x equal to 1 over b minus a on the interval from a to b, right? That would also be a uniform distribution. The function's constant. And we know that integrating this over that should give you 1. And there's some problems in your homework, we have to like find k based on the fact that the integral should equal 1. It's a lot of just taking the integral and setting it equal 1, solve for k. Here, right, we could show it, from a to b of 1 over b minus a. Again, that's a constant, so we just get 1 over b minus a times x from a to b, which is going to be 1 over b minus a times b minus a. Oh, it's 1, like we thought. So a couple things. The expected value here is b plus a over 2. I almost wrote b minus a over 2. It's just the average. Right? If you're saying if the bus is going to take between like 30 and 50 minutes instead, we would expect it to take 40 minutes. The average of those two, 30 plus 50 over 2, which is 40. Here you can also calculate the variance. It's kind of a pain in the butt. There's a special formula for it. I never remember it. And I don't imagine you would really be expected to remember it. It's definitely not in my notes. Is it not in my notes? It's definitely not in my notes, yeah. It's something weird like b plus a cubed over 12 or something like that. It's in the book. The variance, well, we could calculate it, right? The variance should be the integral from a to b of x squared times your function minus the expected value we just found squared. Right, that's the nice, better version of it. I wouldn't worry too much about this. Actually, that's not entirely true. I wouldn't worry about it, but it definitely comes up in problem 1, where they actually calculate the variance of something like this. I guess we could. What time is it? Yeah, we got time. I guess we could do it. Let's find out. For our actual bus example, if I wanted to find the variance would be the integral from 0 to 10 of x squared times 1/10 minus our mean squared. So let's see, that's going to be x cubed over 30 from 0 to 10 minus 25, which is going to be 1,000 minus 0 over 30 minus 25, which I'm going to multiply by 30 over 30 to get 750 over 30, which is going to be 250 over 30 or 25 over 3. So there's your variance. Which I think, let me just double check. I think it's b minus a cubed over 12. Does that sound right to me? Let's check. If I did b minus a, that's 10 cubed is 1,000. Nope, that's way too big. I'd have to check. Maybe it's b minus a squared. That might be better. 100 over 12. That does work. I think it's b minus a over 12. B minus a squared over 12. But I would double check in the book. That might be the variance. But I would say check. I don't remember. It might be b plus a squared over 12. Since here a is 0, it could be either way. Okay. Last thing I'll say about the special probability density functions here is that there is a standard normal distribution. None of your homework problems have anything to do with it. Your teacher might say something about it, but here's what you should know, because it is something that will actually come up in stats, or at least something that would be good to know about in stats. The bell curve looks like this. And well, usually better than that, to be honest, but my drawing skill is not always the best. And where'd you go? Thing I wanted to say. Yeah. Typically, we imagine this peak of the curve, that is where the mean is going to be. And then the standard deviation is, I don't know, something like that far or that far. Now, there actually is a function that is this bell curve. That function, which I'm going to write in terms of x, is 1 over whatever the standard deviation is times the square root of 2 pi times e to the negative x minus mu squared over 2 sigma squared on the interval from negative infinity to infinity. So we shouldn't deal with this, right? No one's gonna ask you to integrate anything here. But what's kind of cool is that if you actually took this, like, so let's say you took a function whose paper. Let's get that. Yep. So let's say we had a function that looked like this. Maybe f of x is equal to 1/3 times the square root of 2 pi e to the negative x minus 10 squared over 2 times 9. The mean here is clearly 10. The standard deviation is clearly 3. Because of the way I've written it. Right? I'm filling in the things I want to know. What's interesting, I think, well, one, the integral from negative infinity to infinity of this whole thing, excuse me, is equal to 1. We can't calculate that. Any computer do it. This function is not integrable. Kind of weird. But then also something that is integrable, although it's a giant pain in the ass to integrate, is the integral from negative infinity to infinity of x times f of x. Well, that's just the expected value, which should be whatever the mean is, which in this case happens to be 3. No, not 3, 10. Sorry, standard deviation. And we actually could, although no one's gonna ask you to, you could actually integrate this with the u substitution. It's kind of weird. All right. What was the other thing I want to say here? So when you see this in your stats class, when someone starts talking about the bell curve, even though you're not doing it, when you start looking at, like, so again, this is later on, if you take stats, which most people have to take stats in some way, shape, or form at this university. When you start seeing the bell curve later on, people start talking about the z table and finding the area under the curve. What you're really doing is you're saying, I'm looking at this shape, I'm using an integral to calculate the area under the curve from somewhere to somewhere, using whatever given mean standard deviation we have. And then someone just calculated that for a bunch of different values. Not someone, you use computers to calculate it so that we can have this table so we don't always have to go and calculate these things because they're really, really not fun to calculate. That's kind of the idea behind what the z table is they've taken this idea here and they've found all the values for lots and lots and lots of particular values. It's neat. It's worthwhile. It's good to kind of know where things are coming from. All right. So we have class Wednesday and Friday. That's kind of it. We can talk about more stat stuff on Wednesday if you all want to, but there's still sections 6.5 and 5.6. I think that's what they are, which are talking about the midpoint rule and the trapezoid rule and how to estimate things and the error formula. So we probably should start, like, I'm happy to entertain stuff from section 9.3 on Wednesday if you all want to, but my plan is going to be to talk about those other sections so that we can get through them. But if you have questions about 9.3, you're certainly welcome to bring them on Wednesday. All right, I'm gonna head over to drop-in. See you all later. Well, yeah, those sections are they're not good for testing anyway. So, well, with knowing that, maybe we'll spend less time on them. They're still homework though, so they're definitely better homework sections than I know there's not, it's really kind of tedious calculation stuff, but they are semi-important just because that's often how things actually get calculated. Like with the integrals we were just talking about, right? No one's actually doing the antiderivative and plugging stuff in. They're actually using approximations to get a very, very good approximation using something like the mean value, the midpoint, or the trapezoid or Simpson's rule to calculate, to approximate them. So there is a point and purpose to those things. They're just tedious. You're welcome. All right. Sprint to the end. Bye. I'll see y'all later. You're welcome, Edgar. You're welcome. Bye.